Okay, good morning all. Today we begin our first lecture for the month of May. We have an entire month of May to go for the semester of deep learning. So we are studying chapter 15, which is about representation, which I believe is one of the most interesting research topics in deep learning. So it's worthwhile to see what are the issues here. We covered one topic last time, which was called greedy layer-wise pre-training, which is a fairly obvious concept that if deep learning is about several layers, can we learn each of these layers independently and put it all together into a large network? So that's a very basic topic. That's how deep learning started out. And so today we look at the next topic, which is referred to as transfer learning. Okay, so there was some background noise. We'll continue. So we are looking at the topic of transfer learning. And here, the issue seems quite straightforward. Is it possible for a neural network that has been trained on a probability distribution P1? So you got a data set characterized by a probability distribution. And you are wondering whether that can be used for a slightly different task. Also similar data. A classic example given is you have defined a neural network for supervised learning to recognize cats and dogs. And now you're interested in a neural network that can recognize ants and wasps, insects. The data set for cats and dogs is plentiful, and data sets for insects may not be that plentiful. Is it possible somehow to leverage what we did with cats and dogs with ants and wasps? The answer is yes, because a lot of the low-level processing, earlier layers, such as edge detection and grouping the edges together to form regions and so on, might all be very similar. So you could leverage all of that. And only at an upper level, you say the objective is different. And so you're using the representation. So this is a lecture on representation. So the representation learned with a large distribution P1 can be used for a distribution P2. That seems like a very practical thing. You don't have enough data, so you just train on one. And there are all kinds of very heavily trained modules available. If you're in computer vision, there is a network called VGG19, trained by a group at Oxford, which they've made freely available. And you could use that trained network to perform another computer vision task. Similarly, in the area of natural language processing, the folks at Google developed this BERT system. It was based on bidirectional transformation or transformer network. And it has been trained on an enormous amount of data which is made available to do other natural language processing tasks of your own, such as you want to do some sentiment analysis, you could use BERT. So that's all transfer learning. It seems like a straightforward engineering issue. But the topic is also at the cutting edge of deep learning because it relates to a fundamental definition of what is machine learning about. Machine learning is not about simply optimizing on a particular data set. It is about generalization. It is to perform well on data that the system has not seen. Well, isn't that what transfer learning is about? That you are going to be running it on data that you have not seen. course, there are some things that are more fixed in generalization idea, that the task is about the same thing. There are no changes on it. So there is a lot of commonality between transfer learning and generalization. And that becomes an issue of defining what are the latest current state-of-the-art research problems in deep learning. And so one of which starts from this point of view about generalization. And so we have the topic of generalization, we have the topic of transfer learning, and then there are these two classical topics that exist in machine learning. When we do studies in machine learning, we learn about supervised learning and unsupervised learning as two different areas, one with annotations or labels and the other without. In the unsupervised learning case, we learn probability distributions. In the case of the supervised learning case, we have annotated data from which we learn how to perform a given task. But this area of transfer learning leads to another area, which is about semi-supervised learning. What if we have some data that has been labeled and a lot of data that has not been labeled? How could we possibly leverage, under what conditions would that be possible to use what is known and use it to use much more data? So it's a combination of unsupervised learning and supervised learning that becomes a semi-supervised learning. So we have all these topics: generalization, transfer learning, unsupervised learning, supervised learning. Then we have semi-supervised learning. That is only some of it is supervised. And then add to all of this mix the latest and greatest topic in research in today's deep learning, which is called self-supervised learning. That's yet another topic, where the issue is not exactly the same as semi-supervised learning, but one where we have some data that is somewhat labeled, not fully labeled. Maybe there are data from multiple modalities coming in. And what you learn from one modality, one type of sensor for a car, let us say, can it use what is learned with one modality with another modality? There seems to be something common about that in transfer learning, but here we have different data, different distributions. So in a sense, it's different from it's a simple semi-supervised learning. It's called self-supervised learning. So anyway, that's another very current topic. We'll touch upon that after we finish our basic discussion of transfer learning. And within transfer learning, we'll begin with distributions P1 and P2. We'll talk about examples in computer vision and natural language processing, which is about BERT and BGG. And after that, we'll talk about some variations of semantics of input and output. So there are certain tasks where the semantics of the output are different. That's what transfer learning is about. But there could also be tasks where the semantics of the input are different. And maybe we have the same goal as the output. So it's semantics of input output. We'll talk about that. And after that, we will talk about some variations called domain adaptation. So domain adaptation would be about what if there is some changes taking place, like the topic is changing as you are discussing something. So we are going from one domain to the next domain, and which is kind of transfer learning. It's almost synonymous with transfer learning, the domain adaptation. So we'll talk a little bit about that. And after that, we'll talk about something intriguing called one-shot learning and zero-shot learning. One-shot learning is a situation where you have only one labeled sample, a lot of unlabeled samples, as long as you have selected an appropriate underlying feature, one can solve the problem even with a single example and accomplish something sounds miraculous, which is one-shot learning. And the other extension of that is zero-shot learning. What if you don't have any samples, but you have some descriptions? Somebody gives you a description of what a cat looks like, okay, rather than give an image of a cat, saying a cat has two pointed ears on top and it's a tail and it's furry and so on. Would that be enough to recognize a picture saying, oh, that's a cat? So that's called zero-shot learning, and it all relates to these areas of not having enough samples. It's worthwhile to look at all of these topics. And the final part of today's lecture will be some indications of future research that relates to transfer learning. And this one has to do with when you're doing the transfer, the representation that you have of the distribution, does it capture all the causalities that exist in the data? Causality is if you have two variables, x and y, you not only know the joint probability distribution of x and y, but you also know whether x is the cause or x is the effect with respect to y. It's an interesting problem. If I give you a joint distribution of two variables, I can extract from it the marginal distribution of each variable. I can get conditional distributions, but I cannot directly tell which is the cause, which is the effect, which requires some kind of external stimulus, such as an intervention, to tell that. And then we can ask the question, what are the practical implications of that? And then we show some results. It's just, these are all emerging things, research topics. And this one shows that if you knew the correct causality in your model, you can more quickly adapt to a new distribution. If transfer learning is about moving from a training distributions to a transfer distribution, we bring in some new words now. Not only do we have a training set and a test set, we have a training set and a transfer set. So we are saying to adapt to the transfer set, if when you're learning the training set, you also learn about the cause and effect relationship that exists, then you can adapt better. Seems like a reasonable thing to know. The more you know about your training distribution, the easier it is to do a transfer. So anyway, those are all the main topics to keep in mind of what is it that we're going to learn today. All right, so I'm going to now begin with the slides, with the slide deck for transfer learning. Okay, so I'm wondering whether I should maximize the PowerPoint, but maybe that will make it clearer. Sure. Okay. So the title is Transfer Learning and Domain Adaptation. I've indicated what these things are. We'll again look at it. And this is just one topic in representation learning. And we have learned greedy, layer-wise, unsupervised pre-training as the first topic. We are on to the second topic, transfer learning and domain adaptation. That is today's lecture. On the next lecture will be on 3, which is semi-supervised disentangling of causal factors. That's extremely important and closely tied to today's lecture. 4 is on distributed representation. That's yet another important topic which talks about the strength of symbolic representation versus distributed representation. And related to that is exponential gains by having deeper networks. And again, back to providing clues to discover underlying causes. So this chapter, chapter 15 of deep learning, is really a nice starting point to anyone looking for a research topic in deep learning. So within transfer learning, what are the subtopics? We'll first define what is transfer learning, and then we'll give the examples of transfer learning in natural language processing and computer vision. And then the topic of shared semantics of input and output. And what is domain adaptation? And then about concept drift as we move from topic to topic. And then the ideas of one-shot and zero-shot learning, where we have only one example or no examples. And then finally, the issue of transfer learning and generalization as a theoretical topic leading to some future work. So what is the definition of transfer learning, also known as domain adaptation? Is that learning in one setting, that is distribution P1, is used to improve generalization in another setting, distribution P2. So this is the classic definition of transfer learning. And in a sense, it generalizes previous topic of greedy, unsupervised pre-training, where we transfer representations between an unsupervised task and a supervised task. So there we talked about how we could have layers learned by unsupervised learning and finally use it for a supervised learning tasks. The same idea in a general way rather than layer by layer. So here is the simple example to fix the concept of transfer learning. In visual classification, we have significantly more data in distribution sampled from cats and dogs. So here are a whole bunch of cats here, and here are a whole bunch of dogs here. Lots of them available on the internet. People like to look at pictures of cats and dogs, but they don't particularly like to look at pictures of ants and wasps, some of which can be pretty nasty. So supposing we want to learn on these and we want to have a system to learn to quickly generalize to ants and wasps to automatically detect them. So transfer learning is to go from one type of problem to another type of problem. And the visual categories of cats and dogs and ants and wasps, they share low-level notions of edges and visual shapes. Maybe the idea of edges around the body, edges around the limbs, and so on, and grouping them together into parts, and effects of geometric changes. So it could be that how the shapes change. And also changes in lighting. You might have different kinds of lighting and shadows and so on. So what you have between the two distributions, P1 is about cats and dogs and P2 is about ants and wasps. And we're talking about transfer learning and going from one to the other. So the practical need for transfer learning is training a deep learning model requires a lot of data and, more importantly, a lot of time. And so it's useful to take advantage of pre-trained weights on huge data sets that took days or weeks to train and leverage it towards our use case. So that makes sense that not in every problem we have lots of data and lots of time. So we want to leverage what we already know. So depending on how much data we have at hand, here there are different ways to leverage this. So here is a nice systems level example of transfer learning in natural language processing. We have on the left-hand side a language model, BERT. This is the Google development, which used tons of data from Wikipedia and books with the objective of language modeling. And they used partially supervised and partially unsupervised and created a language model. And then supposing we wanted to do another natural language processing task, it was not about modeling the language, but specifically we wanted a simple problem of sentiment analysis. And here's a software system called Sherlock, which is a sentiment analysis program that takes a data set of movie reviews saying the movie was good is given 1, the movie was horrible was 0. And we used a pre-trained model here that takes this language as input, and it associates, we got supervision signal available 1 and 0, which is used to train the classifier from the language model. Should it go to 1 or 0? So this is some kind of embedding and all that stuff is going on in the pre-trained model. And so this is an example of transfer learning where all the language modeling, the embedding that you need and all the embedding at several levels and so on is all done. And you're just adding to the top of it the classifier. So this would be an example of transfer learning in NLP. In the computer vision domain, similar thing has been happening. One could be training a robot to look at this scene and so on, and you have a direct learning and you have a classification result. It's a deep learning model. You can say, well, we got to throw lots and lots of data at the problem, and that is what is being learned. And the transfer learning approach says, well, there is a model available called VGG16, I think there's a VGG18, 19, so on, which takes input images and it uses a pre-trained model to create an intermediate representation. And then there is a model on top which takes this information and provides a classification result. So a similar thing that all the heavy duty lifting has been done by the VGG19 model, which is utilized to perform the task we want to do. So in transfer learning, the learner must perform 2 or more different tasks. But we assume that the factors that explain the variations in P1 are relevant to the variations to be captured for learning P2. So we are now using the word factors of variation. That is, that's what these deep learning models do. They're capturing what are the factors of variation. And some of the material we'll cover in the near future is about disentangling these factors of variation. Can you tell clearly what are these factors? Are they independent factors? So this may be entangled factors, but still this is what's being shared. And in the supervised learning context, input is the same, but target is different. There is more data in distribution P1 and very few in distribution P2. So that's what's happening in transfer learning. Okay, so we will move on to shared semantics of input and shared semantics of output. Right. Okay. So transfer learning, multitask learning. You can think of it as multitask learning. So we not only want to use the learning set to perform one task, but also 2 different tasks. Yeah, the example I like to give here is the autonomous vehicle, where the input is from the cameras, and we have to do 2 things, which is to steer the car, and the other one is to press on the accelerator and brake and so on. So the different tasks, but the input is the same, multitask learning. And domain adaptation, which is changes in the output, are achieved via representation learning, where there exist features that are useful for different tasks or settings, corresponding to underlying factors that appear in more than one setting. And this is kind of stated in a general way. So this is a general computational graph. Remember, computational graphs are a general way of denoting the kind of computation that go on in a deep learning situation. We have this diagram. X is the input. It is a very high dimensional input vector. And we learn a representation H, which is shared representation. And that shared representation would be further refined to get hidden representations H1, H2, and H3. And H1 and H2 are being used to produce output representations Y1 and Y2. So this could be the example of, X is a image from a camera, and that is leading to Y1, which is the steering wheel, and Y2, which is the accelerator. And there is also here shown an H3, which doesn't have an output. That might correspond to an unsupervised type of learning situation where we are learning a representation without any task in mind. So this is a shared input. All these tasks have the same input. You can also have shared semantics of output. Sometimes what is shared among different tasks is not the semantics of the input, but semantics of the output. In speech recognition, we need to produce valid sentences at the output. And earlier layers near input need to recognize very different versions of input phonemes depending on person speaking. So we might have, I don't know, maybe it could be different languages or different kind of tonalities. So the input is different. If it's different languages, let's say, or different accents. But the output is the same. Let's say to Alexa, you are talking, and the goal is the same, but we have to deal with different types of input. So that is also a common representation with different inputs. So this aspect of transfer learning with shared output but different inputs, and when the variable y has the same semantics for all classes and x has different meaning dimension for each task, and three users x1, x2, x3 are inputs, and the lower levels up to selection switch are task specific, and upper levels are shared. So we bring it up to a particular level, and after that, the upper levels are shared. So semantics of the output are shared and not semantics of the input, as in speech recognition, where vocalizations are based on different speakers, right? So we might have something specifically trained on a particular speaker. Okay, this is just a little bit of a more on this topic of transfer learning. People have categorized saying ways of leveraging transfer learning. This particular slide relates only to the training data size. And if it is a very small training data size, you freeze all the earlier layers and just the last part, this is the softmax part here, the linear classifier here, and only that part is being trained on a small data set. The rest is all frozen. And if you have a medium data set, you could do the softmax part as well as the previous one part, weights on the last layers is being done. And when you have a large data set, you can train weights on layers and softmax by initialing weights on the pre-trained ones and so on. So this is kind of all kinds of practical things about size of the P2 data set, small, medium, or large. And related to all of this is domain adaptation. So here the input distribution is slightly different. As we already saw in sentiment analysis. Okay, so we talked about BERT and sentiment analysis. Here we're talking about just sentiment analysis, where we're making just a small adaptation. We're moving from domain of media. Maybe we have reviews of books, music, and videos. We have trained it on that. Now we want to train it on the domain of consumer electronics, TV and smartphones. So this is also a sentiment analysis task, but we're just changing the domain. So it's kind of a minor adjustment is being referred to as domain adaptation rather than transfer learning. And there's a little bit more detail being given here. So determine if comment is positive or negative. Sentiment predictor is trained on customer reviews of media, books, videos, and music, and used for comments on consumer electronics, televisions, and smartphones. And so what's going to change is the vocabulary and style varies between the domains. And simple unsupervised pre-training with denoising autoencoders have been found useful with domain adaptation. Right? So that's domain adaptation. Well, related to domain adaptation is concept drift, where there are gradual distributions over time. This has got a name here in probability theory, where they talk about stationarity, that over a period of time, the distribution remains the same. But now we are talking about non-stationarity. Concept drift and transfer learning can be regarded as different forms of multitask learning. And multitask learning typically refers to supervised learning, and transfer learning is applicable to unsupervised learning and reinforcement learning as well. So anyway, these are all terms. So when you change the concept, I suppose you need to slightly adapt to what is changed. So let's praise the success in transfer learning. So it has been successful in machine learning competitions. Particularly, you have a scenario where participant is given data set from the first setting from distribution P1, illustrating examples from some set of categories to learn a good feature space. And you learn transformation applied to inputs from transfer setting, a linear classifier trained to generalize well from a few labeled samples. Perhaps the experiment is set up such that, or the competition is set up where you're given some time to train on P1, and then you're given a short period of time to train on P2 and see how well you do. With deeper representations in learning from P1, learning curve on P2 becomes much better. So these are all practical issues. So the extreme forms of transfer learning are one-shot learning, where only one labeled sample is given, and zero-shot learning, where no labeled samples are given. And in one-shot learning, we have a single labeled example of the transfer task, and it is possible only because representation learned to separate classes during stage 1. During stage 2, only one labeled sample was needed to infer label of test examples that cluster around the same point. So this says that the representation that was learned was rather nice. It learned a representation where the categories fall apart. They're nice multimodal along that particular feature. And if I give you just one sample for each mode, it can discriminate between the two. And works to the extent that factors of variation corresponding to invariances have been separated from other factors in learned representation space. And I'll give you an example, maybe here or in the next set. Maybe here, I'll just mention it. Supposing I was looking at the problem of recognizing whether the character, we're trying to, let's do doing optical character recognition, whether the character is uppercase, lowercase, or a digit, 3 classes. So uppercase are usually larger, lower cases are usually smaller, and digits are in between in terms of, let's say, the amount of ink consumed in printing the character. So there are really 3 different classes here: uppercase, lowercase, digit. And if you just had a single feature which corresponded to the amount of ink in that character. So we are measuring amount of ink in the character, and we look at the distribution of ink for the three classes, uppercase, lowercase, and digit, you might well find that the ink consumed is smaller for the lowercase. So it forms a small peak on the lower side of the feature. And the digits are in between. So you find another peak in the middle. And uppercase are bigger, so they consume more ink. So they form another peak on the higher side of things. So there are three peaks in this distribution of ink. And all we have is that feature. And we have no label data that we throw uppercase, lowercase digits at the system, and it has just looking at the amount of ink used. It doesn't know anything about which class each belongs to. It says this distribution has three peaks. It automatically learns that there are three peaks here. And now if I give you one example of a lowercase digit, it says, that belongs to my first peak. Okay, so now you know all of distribution of lowercase. And then I give it to you one example of uppercase. Okay, that's my right extreme. Then I give you one example of a digit. So that's my middle one. So with a one shot, I've figured out how to classify uppercase, lowercase, and digits because we knew the distribution in an unsupervised way. Not only that, the feature that we were using is a good one, that it is separating out the classes. If we had used something else that was irrelevant, like, I don't know what, dark or light colored, that might be meaningless. The amount of ink was a very critical feature, which was a discriminatory factor. And one-shot learning is possible if such a feature is there. Zero shot is no labeled examples. A learner reads a large collection of text and then solves object recognition problems. It's like having read that a cat has 4 legs and pointed ears. The learner guesses that an image is a cat without having seen a cat before. I suppose if a cat maybe is too common, maybe we described a particular dinosaur, Pletosaurus or something like that, which, you don't have an idea what that particular dinosaur looks like, but I describe it to you. And then when you see it, you would say, okay, that must be this Pletosaurus. And because it has got the features you just described. So you have not been given an example in that particular image domain, but it has come from another domain. In a way, this is a bit like the new topic of self-supervised learning, where from a different modality, you've got some information. We are just transferring it over to the domain where you don't have any annotations. And this is how the current hypothesis, how do humans learn? And we have very few samples or maybe even no samples. Still we are able to do something with it. We refer to it as self-supervised learning, where we are able to classify things. And then when we are given more and more Pletosaurus, we're saying, those are all Pletosaurus. Now we can ourselves learn what a Pletosaurus looks like in fine detail, even though nobody sat and annotated it. So that becomes the topic of self-supervised learning, the new hot topic of machine learning and artificial intelligence. So zero data learning explained, possible because additional data exploited. So the zero data learning scenario includes 3 random variables, traditional inputs X, which is unlabeled text data containing sentences such as cats have 4 legs, cats have pointy ears. And the traditional outputs, y equal to 1 indicating yes, y equal to 0 for no, and the description of the task represents questions to be answered. Is there a cat in this image? And the model is trained to determine the conditional P of y given x, and T is the task. So the zero shot requires T's representation allows generalization. T cannot be just a one hot code indicating a category, instead a distributed representation of the object categories. by using a learned word embedding and so on. So there are some caveats on zero-shot learning. So this phenomenon happens in machine translation. We have words in one language, and the word relationships are learned from a unilingual corpus, one language. And we have translated sentences that relate words in one language with words in the other. And no labeled word translations available. Word A in language X to word B in language Y. So we don't have a word-to-word translations, but we have some translated sentences. And we can guess translations for word A because we have learned representations for words in X and for words in Y and created a link between the two spaces. So this is the kind of thing that can happen where we are doing machine translation by no examples being given, or there is no one-to-one correspondence. So zero shot as a form of transfer learning. So this principle explains multimodal learning, capturing a representation in one modality, a representation in the other, and the relationship between pairs consisting of one observation X in one modality and another observation Y in another modality. And it learns three sets of parameters: X to its representation, Y to its representation, and relationship between the two representations. So we are talking about languages here, and it learns a relationship between the two. And this diagram illustrates this issue. Transfer learning enables zero shot. So labeled, unlabeled examples of X. We have got here on the left side, everything about X, and this is about Y. And we have labeled, unlabeled examples of X allow learning a representation function f of X. So this is the space of X below here. And this is the mapping f of X, which maps it to the hidden values. And similarly, we have here Y through functions fy going to the hidden values. And each application of fx and fy appears as upward arrows, and distances in hx and hy spaces provide a similarity metric. And images x test is associated word y test, even if no image of that word was ever presented. So we are dealing with some kind of a hidden representation where there is some analogies going on, even though there are no images. And we can learn to perform the image mappings in zero-shot learning. Okay, the last part of today's lecture is about transfer learning and generalization. It says, current machine learning methods are weak to generalize beyond the training distribution, which is what is needed in practice. That's a very powerful statement that's being made. Just what is machine learning? It's not just about optimization, it's about generalization. So we need to go beyond the training distribution. And that is what machine learning is supposed to do. And we are saying here, they are not that good at it. Who says that they're not that good at it? Actually, it is said by a theorem called the no free lunch theorem, that if I give you some samples, you cannot generalize to any possible distribution that they could have come from. Because I can create all kinds of distributions which you were not anticipated in what you have seen. So there is no algorithm that can perform well with any possibility. Okay, so you're making some assumptions. That's what regularization is all about. To saying, okay, we're going to generalize to some extent with whatever priors you give me. So that's about the generalization capability of machine learning. This one is saying, can we approach this? Can we approach it? Can I give you some information about how the distribution is going to change? So that might be a powerful way. So that is what transfer learning is about, isn't it? Because we say we have a distribution P1 and we need to adapt to P2. So then we can ask the question, how is P2 obtained? Can it be obtained from P1? Can you specify the changes that have taken place? And that's what we address here. So one more criterion we bring in here is fast transfer learning. That we want to adapt quickly to some change here. So what has been learned previously is a rich base to adapt to a new but related distribution. Some new concept may have to be learned, but because most of the other relevant concepts have already been captured, learning can be very fast in the transfer distribution. So you may need to learn a few new concepts. Whatever these H's are, they're all the features H1 through H whatever number of latent variables. They're all referred to as concepts. And we might need a few more concepts, but a lot of them have already been captured. So assumption on the changes. So changes are sparse when the knowledge is represented in an appropriately modularized way, with only one or a few of the modules having changed. So there are modules for computing the hidden values, but only some are being changed. And the distributional change is due to actions by one or more agents where a single causal variable is clamped to a particular value. So people have looked at this issue of causal models where we have some kind of an external force that is changing some variables. And if you can model that, that's useful here. So the need for inferring causal structure. So why do we need to infer causal structure? And that's being explained in the slide. A possible change to the joint distribution due to an intervention. And it is insufficient to learn joint distribution of observed variables. It is saying that if I tell you that the variables are x and y, if I know the joint distribution of f and x and y, which means I know for every combination of x and y, what's the probability. That is not enough. And we should also learn about the underlying high-level variables and their causal relationships. And this is brought home in a very nice example here. You know, today in this medical world, everybody's familiar with medical world, COVID and all that, right? The medical world is full of these ideas, but let's take a simple non-medical example. Causal relationship. Let's say the variable A is about rain, and the variable B is about opening an umbrella. Right? So we can say intuitively, the variable A causes variable B. Raining is what causes one to open an umbrella. It's not the other way around. We don't say that just because people opened umbrellas, it started raining, right? So the causality is in one direction and not both directions. So if I give you the probability of A and the probability of B, and then if you tell me that they're correlated, that when the probability of raining goes up, probability of opening umbrella goes up, sure, they're both correlated variables. And I give you how often both rain and open umbrella are true, and both rain and open umbrella are false, and the other combinations I can give you. That's a joint distribution. But the joint distribution doesn't tell you about the cause and effect. It's an interesting problem that simply if two variables are correlated, it doesn't say anything about, of course, the causality information. But not only that, it doesn't even tell you the direction of causality. But here is a scenario where we can learn the causality. Supposing we change the probability of raining because the weather changed, all right? So we went from, I don't know, from January to June. and the rain probability may be increased. Um, so the relationship between A and B doesn't change. That is opening umbrella given that it's raining. But it has an impact on the marginal P of B. So if you change the probability of raining, change the probability of A, it has an impact on B, which is exactly causality. So A influences B. So when the amount of rain increases, the probability of opening umbrella increases, but it does not change the relationship that when it rains, you open the umbrella. So this is the direction of the causality. Conversely, an agent's intervention on B, so we have no idea. We are an outsider who don't know anything about umbrellas and raining. And we cause an intervention on B, and say people go outside and open your umbrellas. And we find that when people open their umbrellas, there is no effect on whether it's going to rain or not. So we say, well, okay, by that intervention, we learn that there is no effect between B and A, but there is an effect between A and B. So even though I gave you a probability distribution of A and B, from which you could say nothing about which causes what, but by giving an intervention, you can learn that the directionality is A to B, not B to A. And that asymmetry is not visible from A-B training pairs until an intervention. So motivate setup where one learns from a set of distributions arising from not necessarily known interventions, not simply to capture a joint distribution, but to discover some underlying structure. So we are bringing in a new ingredient that deep learning is not just about marginal distributions, joint distributions. There is also something more here, which is about the causality between variables. So advantage of correct causal model. So why does it matter that you learn causality? Supposing A and B are discrete with n possible values, right? So this is being illustrated with an experiment to see whether it matters if you know which is the cause and which is the effect. So consider two parameterization, A to B model and B to A model. Those of you familiar with probabilistic graphical models know that the joint distribution of A and B, I can write it as a graph with two nodes. One is the node corresponding to A, and the other one is a node corresponding to B, where a directionality of the arrow goes from A to B. This means A is the cause, B is the effect, and the joint probability distribution represented is P of A times P of B given A. That's the first equation here, is the causal model A to B. If I write B to A, then we have probability of B times probability of A given B's. And so I have two different ways of representing the same joint probability distribution. And the number of parameters needed to represent these distributions is of order n squared, where n is the number of possible values of A and B. And you would need a table for every combination of values of A and B for the conditional distribution. So you would need n squared parameters. Of course, for the marginal A, you'd need another n parameters. So the n squared plus n is order n squared. And maximum likelihood estimation leads to indistinguishable test set performance. If you simply went about doing, maximum likelihood estimation of the parameters, you would say, well, it doesn't matter. A to B or B to A gives you the same performance. So the causality doesn't matter is what maximum likelihood will tell you. So now we are actually comparing the two models, A to B versus B to A. And it says how fast the models adapt on a transfer distribution after being trained on a training distribution. So they went about using stochastic gradient descent and the likelihood function and all that. And assume that A to B is a correct causal model. And we assumed that, and then we are using the change between the two distributions is a random change in parameters. So they are changing the distribution, and the model, correct model is A to B, and then they test it on the model that assumes A to B, the model that is B to A in the original learning distribution. And they draw an extremely interesting graph. By the way, this paper is kind of state of the art. I found it, the paper by Bengio and his multiple co-authors. It's a 2019 paper. And both Bengio, who won the Turing Award last year, as well as Jan LeCun, they're pretty big on this. They're on this topic of self-supervised learning. And this seems to be one of the motivating things there. And here, this graph is interesting, that the pink region is the wrong assumption, B to A. The blue region is the correct assumption, A to B. And they're adapting a task, assuming the correct distribution or the wrong distribution, in the sense directionality. And it says, well, after a long period of time, both are the same. They learn the correct concept. But early on, the correct model learns much quicker, and the other one goes really wrong and finally starts picking up. So this is an ensemble over a lot of different kinds of distributions and so on. It's kind of a very large set of cases averaged together, but it does show that knowing the correct causality in the property distribution may be of some value, which is kind of very interesting. We'll again use this concept in the next lecture, which will be on semi-supervised learning and to learn to disentangle causal variables. That's going to be the next topic. Okay, I'm going to stop at this point and invite any questions you might have. Okay, so all right. Okay, since there is some issues with the muting and so on, we're going to terminate the class now. And please do send me any other queries you might have.